isotopes produces the largest amount of energy compared to all other conceivable reactions between light atomic nuclei. The deuterium-tritium reaction takes place according to the following principle. The two atomic nuclei fuse to form a helium nucleus, and additionally, they set free a neutron. This causes a large amount of energy to be.
The Sun and Earth both emit electromagnetic radiation. This movie will help you describe the differences between the types of radiation emitted by the Sun and the Earth. Electromagnetic radiation is energy that travels in the form of electromagnetic waves. Different types of electromagnetic waves carry different amounts of energy. The shorter the wavelength, the more energy carried by the wave. The wavelength of emitted radiation is determined by the temperature of the object it comes from. The higher the temperature, the shorter the wavelength of emitted radiation. The Sun, with its high surface temperature, emits a great deal of high-energy, short wavelength radiation. Energy emitted by the Sun is also referred to as solar or shortwave radiation. Most of solar radiation is the visible light we see with our eyes, but it also includes wavelengths that we cannot see, like the ultraviolet light that causes sunburn. The Earth, however, being much cooler than the Sun, emits lower energy, longer wavelength radiation. Energy emitted by the Earth is also referred to as terrestrial, which means land-based, or long-wave radiation. Although we cannot see long-wave radiation with our eyes, we detect it as heat. In summary, the types of radiation emitted by the Sun and the Earth are determined by their temperatures. The Sun, which is very hot, emits high-energy, short-wave radiation, while the Earth, which is much cooler, emits lower-energy, long-wave radiation.
White light from the Sun is made up of all the wavelengths of colors in the visible spectrum. When we point the probe at the Sun, the spectrophotometer shows full intensity of all wavelengths in the visible spectrum. You may also expect a white light bulb to emit all the colors in the visible spectrum. However, when we use the spectrophotometer, it shows that some wavelengths are not emitted as much as others. Here is that red ornament under sunlight. Now it is easier to see that the ornament does reflect red wavelengths of light. Compare how the ornament's reflected light is different under the white light bulb than when it is under the Sun. This illustrates how the properties of light are not always consistent with what we see. Another example is when we mix colors of light on the surface of a table. The combined emissions from a green bulb and a red bulb look yellow. However, the probe does not show that yellow wavelengths of light are present. So why do we see yellow? You are probably familiar with how paint combines to form additional colors. The primary colors of red, yellow, and blue can be combined to create other colors, such as orange, green, and purple. This is called a subtractive model. However, when we mix light, it follows an additive model. The additive model is also called the RGB model because when we combine the primary light colors of red, green, and blue, it produces additional colors such as magenta, cyan, and yellow. We can use the RGB model to explain why combining red and green light appears yellow. You also investigated how light is transmitted through colored water. The spectrophotometer shines white light through the cuvette and measures the absorbance and transmission of the light when it passes through the liquid. You probably expected the yellow wavelengths to be transmitted, but with your knowledge of the RGB model, you should also understand why green and red wavelengths are also transmitted. What wavelengths are absorbed by the yellow water? Transmittance and absorbance have an inverse or opposite relationship. So the wavelengths that are absorbed are those that are not transmitted.
Earth's greenhouse effect greatly affects climate. See if you can describe how carbon dioxide and water vapor cause the Earth's greenhouse effect. Also, see if you can describe how the greenhouse effect maintains the surface temperature of Earth. Scientists have long known that the presence of an atmosphere keeps the surface of the planet warmer than it would be without an atmosphere. In fact, without an atmosphere, the surface of the Earth would be about 30 degrees Celsius cooler than it is now. In order to understand why, we need to consider the surface of the Earth and its atmosphere separately. Because there is a radiative equilibrium, we know that the planet emits enough long-wave radiation into space to equal the solar radiation absorbed by it. However, most of the long-wave radiation that is emitted by the planet into space is emitted by the atmosphere rather than the surface of the Earth beneath it. Although the surface of the Earth does emit long-wave radiation, only about 10% of this radiation passes through the atmosphere and escapes into space. The rest is absorbed by clouds and by greenhouse gases in the atmosphere. There are many greenhouse gases, but the most abundant greenhouse gases are water vapor and carbon dioxide. Short-wave radiation from the sun passes through greenhouse gases, but long-wave radiation is absorbed by them. Greenhouse gases absorb long-wave radiation that is emitted by the surface of the Earth. Subsequently, they re-emit the energy as long-wave radiation in all directions. About half of the re-emitted long-wave radiation does escape into space and contributes to the planet's radiative equilibrium. About half of the long-wave radiation emitted by the gases is directed back toward the surface of the Earth. As a result, a continual exchange of long-wave radiation takes place between the surface of the Earth and the atmosphere above it. The long-wave radiation contained in this exchange causes the warming effect known as the greenhouse effect. This phenomena is known as the greenhouse effect because, like the glass in a greenhouse, the atmosphere traps some of the energy beneath it. The greenhouse effect produces a warmer climate on Earth than would be possible without an atmosphere. In summary, water vapor and carbon dioxide allow solar energy to penetrate Earth's atmosphere but prevent much of the long-wave radiation emitted by the surface of the Earth from escaping to space. This trapping of long-wave energy is called the greenhouse effect and enhances the surface temperature of the Earth.